بسم الله الرحمن الرحيم. محاضرة بعنوان Combined Free and Forced Convection of Air in a Vertical Annulus with a Uniformly Heated Rotating Inner Cylinder. Abstract. Numerical results of a finite difference scheme are presented for the developing combined forced free laminar boundary layer flow in a vertical concentric annulus with uniformly heated rotating inner cylinder. The effect of superimposed aiding or opposing free convection on the developing tangential velocity profiles is investigated for a fluid with the Prandtl 0.7. Heat transfer in concentric annula with the rotating inner cylinder is of a particular interest to the industry in the design of various types of machinery which involve heating and or cooling. An example of such equipment is a rotating electric motor, which is heated by bearing friction losses and ohmic dissipation of electric energy in the windings, and is cooled by the convection of heat from the surface to the surrounding fluid. The present study is attempted to investigate the free convection effects on the developing laminar upward or downward flow in a vertical annulus with uniformly heated rotating inner cylinder and adiabatically insulated stationary outer cylinder. No available papers have dealt with tangentially developing laminar flows in trans region or vertical concentric annula with rotating inner walls under above boundary conditions. Assumptions. The two-dimensional flow is assumed to be steady, x-symmetric, laminar of an incompressible Newtonian fluid, air, with no internal generation, with constant physical properties except the density which only varies in the gravitational body force term according to the Poisson's approximation, with no viscous dissipation and axial conduction of heat. Governing equations. The equation 1 is continuity equation. The equations 2, 3, and 4 are the momentum equations in r, z, theta direction respectively, and the energy equation. Boundary conditions. The velocities on the surface, outer surface of outer cylinder equal to 0. The velocities at the inner cylinder equal to 0 except the value of W, which is equal to 1. Adiabatic at the outer cylinder and constant heat flux at the inner surface cylinder. This figure shows a great generation. Numerical formulations. It may be worth mentioning that the choosing finite difference approximations are not perfectly symmetrically, nor are they of the same form in all the equations. This is does so as to ensure stability for the numerical solution. Results and discussion. This figure shows development of the axial velocity profiles along the annulus for aiding flow with radius ratio 0.555, heat flux 100 watt per meter square, Reynolds number 200, and the values of Reynolds square over Taylor number equals to 0.2. As shown in this figure, the velocity profile is maximum at the near to the inner cylinder. At the outer cylinder or near the outer cylinder, some particles of fluid may be moves down towards the entrance. If the value of Reynolds number is 1,000 at the same values of heat flux and radius ratio and the values of Reynolds square over Taylor, the behavior is changed to the following behavior. The maximum velocity occurs near the inner rotating cylinder. This figure shows development of the axial velocity profile for constant heat flux aiding flow with radius ratio 0.555, Reynolds number equals to 500, Reynolds square over Taylor equal 10. This figure shows the effect of heat flux on the development of the axial velocity profiles. As shown in this figure, that as heat flux increases, the value of velocity profile is higher than that heat flux in the lower value. This figure shows comparison between aiding flow and opposing flow for the development of the axial velocity profiles along the annulus for aiding and opposing flow. This figure shows the effect of heat flux on the developing of temperature profiles for constant heat flux aiding flow, radius ratio 0.555, Reynolds square over Taylor equal to 10. This figure shows the development of the temperature profiles at various cross-section of the flow along the annulus with value of heat flux equal to 100 watt per meter square, Reynolds number equal to 200, Reynolds square over Taylor is 0.2 value. This figures shows the effect of Reynolds square over Taylor value on the developing or on the tangential velocity development along z-axis for forced convection with radius ratio 0.555, heat flux equal to 50 watt per meter square, Reynolds number equal to 200 with radius ratio 0.1. This figure shows a comparison between opposing flow, forced flow, and aiding flow of the tangential velocity profile along Z for radius ratio 0.555, as shown in this figure, that the value of opposing flow gives higher values of tangential velocity development. These figures shows local Nusselt number versus dimensionless axial distance for constant heat flux. The first figure shows the effect of heat flux. The second figure shows the effect of Reynolds number. As shown in these figures, that the local values of the local values of Nusselt number increases as heat flux increases, and as Reynolds number decreases. Conclusions. The fluid accelerates near the heated wall and accelerates near the opposite insulated wall in aiding flow case, and vice versa in opposing flow case. There is a little effect for the parameter Reynolds square over Taylor on the fluid flow and heat transfer process. The growth of the thermal boundary layer along the annulus increases as heat flux increases and Reynolds number decreases. The free convection effect is absent at the entrance and appears downstream, leads to improving the heat transfer process as heat flux increases. شكرا يا صاحبي. أستاذ المساعد الدكتور عقيل عبدالله محمد، تدريسي في جامعة النهرين، قسم الهندسة الميكانيكية.